Hello everyone, my name is Joanna, and in this workshop I am gonna show you how to create interactive virtual acoustic environments in TASCAR. So let's start. The agenda of today's tutorial will be the following. First, I will tell you something about the motivation behind creating the TASCAR tool. Then I will tell you in a bit more detail what is TASCAR, and then I will show you step by step in a tutorial how to create a TASCAR scene. After that I will give you several examples of applications, and we at the end will come to conclusions. So let's start with the motivation. So in Oldenburg, in the research group I am working in, auditory signal processing and hearing devices, we are mostly interested in improving hearing devices. And of course, to be able to improve those devices, we need to know quite some details about how they work, and therefore we need to do reliable research to know how they behave in various situations. But the problem here is that the performance of these devices, performance of some hearing aid algorithms that is measured, is usually measured in the lab, and the results that are measured in the lab, they don't always reflect how those devices really work in real life. So here in these two pictures you can already intuitively see the difference. So the results that we obtain in this environment on the left side, in a sound booth, in a cabin, will be very different than how the hearing aid or a different hearing device will work in a busy street. So there are several factors that influence this gap. So first thing is the stimuli itself, so the sounds that we can experience, we can hear in those two environments. So in this lab environment, the sounds will be limited. For example, the room acoustics will not be really taken into account, or also on the street there are various types of moving sources, dynamic scenes, which will also not be simulated in the lab usually. So the stimulus itself is an important factor that makes those two environments very different. And the second thing is the behavior, which means that in real life, in the wild, so to say, we as listeners take an active role in the acoustic scene. And therefore we can also influence by, for example, our head movements, or also by our communication with others, influence that acoustic scene. And here you can see another graph that represents this trade-off. So on the left side we have objective analysis in the lab, in a traditional lab, which gives us a lot of sensitivity, so we can have very reliable results with that type of measurements. But of course the complexity of these scenes will be limited, and therefore validity of these scenes will also be limited. Whereas on the right side you can see this street environment, which gives us also the field measurements, which gives us high validity. So it's very similar to what it is in real life, but it basically does not give us much control or sensitivity. So the motivation is to create something which we call here an advanced lab, so something in between those two extremes. So a lab where we will be able to create more realistic scenarios and also include the subjects, the participants of experiments in the communication loop. But still, we want to still have the control, to keep the control over the experiments, and we want to make them as reproducible and controllable as possible. Okay, so that was the motivation, and with that motivation, a tool called Toolbox for acoustic scene creation and rendering was created. And this TASCAR tool is an open source platform for real-time interactive virtual acoustic environment rendering in laboratory environments. And what can we do using TASCAR? So with TASCAR, we can create those virtual acoustic environments with moving objects. Then we can interactively explore those environments, and we can also render them in real time and use an arbitrary playback system to play back those scenes. So you can already see that with such a tool, it will be easier to create a realistic environment for testing the subjects with hearing devices or the hearing of the subject itself. So here we can see another representation of what TASCAR is, and in this block diagram you can see the main part of the block diagram is the virtual acoustic environment, and this is what I will today show you how to create, and we will call it sometimes the TASCAR scenes. So TASCAR allows for creating the arbitrary scenes. You can see that in this TASCAR environment we can put various objects like diffuse sources, point sources, reflectors, or receivers, and also we can feed those sources with the various sources of sound. So here you can see it in this lila color on the left side. You can see that the sources within a virtual acoustic environment can be fed with a wave file, with sounds generated in Matlab or in other software. Also with, for example, an established speech intelligibility test, or even with a signal from a microphone in real time. So then we of course have some kind of geometry processing of that scene, and this geometry and also other parameters, they can be accessed by various external tools. So for example, we can access the parameters of the scene using Matlab, which I will show you today, but we can also steer the geometry of chosen objects from the scene using, for example, head tracker or a game controller. And then in the end, on the right side, you can see that this scene is decoded and then can be forwarded to basically any physical reproduction system. So it can be played back with headphones, it can be also saved as a wave file, or it can be sent to a loudspeaker array of basically arbitrary loudspeaker system. So this is what TASCAR is, and now I will go to the tutorial, and in this tutorial I will show you what is actually this TASCAR scene, how does it look like in this software, how to put point sources, diffuse sources, reflectors, receivers and reverberation into that scene. I will show you also some additional modules which allow us for some additional functionalities, and I will also show you how to communicate with such a scene with Matlab, and at the end I will mention some command line tools that can also be useful. Okay, so we will start our tutorial with opening TASCAR. For that we will open a new terminal, and first I will go to the directory where I created a TASCAR example, and then I can open it by saying TASCAR and then example.tsc. So .tsc is the extension that every TASCAR scene will have. So let's press enter. We will not need at the moment. So what we can see here, we can see some kind of a spatial representation of an acoustic scene. You can see that there are some sources, some receivers. This I will go back to later. But well, the idea here is that we have this scene with certain sources, and we want to create with this tool. We want to create the sound that we would hear as a listener if we were really located here in the scene as this head, which represents the receiver. So maybe the best way to show it, to demonstrate it, is to just play the sounds. So for that we will have here the receiver, and I also have a simple controller that with which I will be able to control the movement of this receiver. So as I change the position of the receiver, the sound will also change accordingly. So let's try that out.
The appearance of the island when I came on deck this morning had changed. Although the breeze had now utterly ceased, we've made a great deal of way during the night, and we're now lying becalmed about half a mile to the southeast of the low eastern coast. Gray-colored woods covered a large part of the
even tint was indeed broken up by strips of yellow sandbreak on the lower land, and by many tall trees of the pine forest, outtopping the others, some singly, some in clumps.
Outtopping the others, some singly, some in clumps.
So I hope you get the idea now. And second thing I want to mention at the moment is we have the so-called map view, and we also have a mixer view. And here we will see the mixer where all the sources, the elements of a scene can be accessed, or at least their gain and their gain can be changed, and we can also mute them or solo them. So let's try that again.
All were strangely shaped, and the spyglass, which was by 300 or 400 feet the tallest on the island, was likewise the strangest in configuration,
like a pedestal to
running up sheer from almost every side,
The
and then
Hispaniola
suddenly
was
cut
rolling
off at the
separate
top
under
like a
the
pedestal to put a statue
The beams were tearing at the blocks, the rudder was banging to and fro, and the whole ship
under in the
creaking,
ocean
groaning,
swell.
and jumping like
The
a
booms were
manufacturer.
tearing at the blocks, the
I
rudder was
became tight
banging
to the
to and fro,
backbone.
and the whole ship creaking, groaning.
So I think you also get the idea. I could influence the gain of various sources, and I could mute them individually. So that was our TASCAR scene and how it looks in TASCAR. And now the question is, how is this scene created in TASCAR? And to answer that question, I will open yet another terminal, and I will go to the same directory as I was before, and I will open the same file, but now I will open it using a text editor. Yes, so I'm using a gedit editor, and here you can already see the TASCAR scene, which is written in the so-called XML file format, which you might know, for example, from creating websites like HTML. So this is a kind of a programming language or language of instructions that will be both understandable for us when we look at it, so we can quickly recognize what's in there, and it will also be then interpreted by a machine. So this XML file, it consists of elements which are here in green, and those elements have attributes. So elements and attributes, it's by those two things we will define the whole scene. So for example, we have an element author, which has an attribute which is like a parameter, and here the attribute is a string, it's a name, which is Joanna Luberacka, and so on and so on. So what can we do here? So we can already see that the XML, our XML TASCAR file starts with a element session, and this will be a root element, which means all the other elements will be included in that element, which means it starts here and it ends at the very end of the whole file. Everything else will be included here. So here we can already specify the license, also the attribution. We can also specify the duration of the scene. And as following sub-elements, we have authors, and we have a scene. So scene is this very important sub-element, where inside the scene, again, we will define all the objects that we want to place in this virtual space. So our scene is called cafeteria, and it will be rendered with the image source model order of 2. Okay, and then so first objects that I would like to tell you about are the point sources. So the point sources, we can see here we have 2 point sources. One is called Peter and one is called Kerstin. So the point sources have some kind of a position and orientation, which is a common sub-element for all the objects. So all the objects in the scene, they will have some position and some orientation. Also, what point sources are, so maybe I will go back here and show you those point sources. We can see point source Kerstin and Peter, and they have a certain position which is exactly specified in that place. So as you can see, it has 4 numbers, because if we wanted to so the first number is time. So if we wanted to create a certain trajectory, we could for example copy this thing and say in the second number 1 the source will move to this position, and the position is specified as you might think in Cartesian coordinates. Okay, so and then we have orientation, and what else do point sources have? So point sources also have the type, which will make their directionality different. So these 2 point sources are, for example, this one, the Peter will be a cardioid source, so point source with cardioid directionality, and the Kerstin is an omnidirectional source. So this directionality will be very useful for speech sources, which in real world they usually are they have a certain directivity. They are not omnidirectional, as the sound propagates only in a certain direction from our mouth. Okay, so one more thing I wanted to tell about the point sources is that we can feed them with a sound file. So here we assigned the file named this M1 script 1 clean to Peter, and a different file name to Kerstin. Yes, and we can also say with which level we want them to be. So much about the point sources now, and then we go to diffuse sources. So diffuse sources also have a name and position and orientation they will also have, and we can also, so maybe I will show this diffuse source. Diffuse sources here, they will be defined as a volume. So basically as a volume in which this diffuse source will be active. Here you could hear in the example the bubble noise. It was our diffuse source in this case. Here you can see the dimensions of this volume where the bubble noise was active. And so diffuse sources are defined as a volume, and also they can be fed with a wave file, but in this case this wave file has to be not a monofile as in the case of point sources, but it has to have 4 channels. It has to be first order ambisonic 4 channel signal, and then it can be fed with a file. So what other objects do we have in this scene? Next thing, next object which we can put in the scene are the reflecting surfaces. So in our scene we have 2 types of reflecting surfaces. One is the shoebox room, so everything is located inside this shoebox room that is defined with or generated with these elements. And we also have a second reflecting surface. It's this table here, and this table is defined by specifying the vertices of the surface. So one way to quickly define the arbitrary surface is, for example, we could do it with other tools like Blender, and then export the vertices from Blender and then copy them or include them in the TASCAR scene. So that would be the way to generate some more complex reflecting surfaces. So the next object that we are interested in and that we have to put in our TASCAR session is the reverb. So in TASCAR, the early reflections are generated with the image source model, but the late reverberation has to have a additional method to generate the late reverberation. And this method of creating the late reflections will be specified here with the element reverb. So one way of doing this is by using the simple feedback delayed network that is now built in TASCAR, for which we also specify the volume. And the second way of doing this is to use the convolution with the first order ambisonic impulse response, which we'll call, this is the alternative approach, which will be called FOA conv, and here the type is simple FTN. So with this reverb element, we will create a late reverberation for our TASCAR scene. The final element of the scene is a receiver. Here it's called out, and it encodes the signals of primary sources, image sources, and diffuse sources into receiver output format, which will be specific for different receiver types. So it can be imagined as a kind of a virtual microphone that captures all the signals that are active in the scene, and then mixes them then in a way that we receive a certain output format. For example, mixes them in a way that at the output we have a binaural signal, or at the output we have a signal that we can forward to a loudspeaker array. So as I already mentioned, in a way, is that there are different receiver types, and here we can see the type of a receiver is the ORTF, which is a stereo output format. But this output format is suitable for listening with headphones, but we can also have, for example, a binaural simulation, which will be called HRTF here, and we can also have various other receiver types that will be suitable for playing back with loudspeakers. Yes, so this was our scene. I also wanted to show you the receiver, but I already said the receiver is here represented as this head, and now I want to tell you something about the external modules. So these external modules that will be located here in the element modules, they provide some additional functionalities. For example, what you could already see before, this simple controller where we steer the head of where we still steer our receiver, it is also generated with the module called simple controller. And then the second example of modules that I have is I have also here this blender scene, and as I will demonstrate in a second. Now we are very far away from the table, but we go back. Oh, I cannot rotate. Yes, so now we are able to see on the left side our Kerstin and on the right side Peter. Of course, this is a very simple scene, but what you can see here, oh, they lost their hair, but what you can see here is that both the visual scene and the acoustic scene will be combined together, and maybe I can also demonstrate it by playing back the scene again.
Something like a manufacturing. I had to cling tight to the backstay, and the world turned giddily before my eyes. For though I was a good enough sailor.
So this functionality allows us. So these are two external models called position to OSC, and also a system module which basically execute any system commands that we want. So with those two modules, we can send the geometry data from the scene so that it can be accessed by an external software, for example by Blender in this case. So while we are moving with the simple controller and in the same time changing the geometry of our receiver, this data is being sent and accessed by Blender, and therefore we can simultaneously change the visual scene. So this is what I wanted to tell you about the external modules. There are various external modules that can be accessed, and one last thing that we can put inside our scene are the jack connections. So what I still didn't tell you about TASCAR which is quite important, is that it uses the jack audio software, which is an external tool, which basically is an audio server that manages all the connections between audio sources in our computer. And here you can see output and input for ports, for example, that the signal of my voice captured by my computer is sent to another jack port. In this case, it's a port for the for this recording, for recording this tutorial, so it does not have anything to do with TASCAR. But well, maybe another example, the sound from TASCAR is also sent to the port so that it can be recorded, so that this tutorial can be recorded. So important thing, these connections can already be made inside the TASCAR scene, so that we basically don't have to go to here and connect or disconnect anything again, but it will be done automatically, which is very helpful. Yes. Okay, so I think I told you everything about the creating the TASCAR scene, and now we will go to discuss the how to access the parameters of the scene using Matlab. Okay, so let's start the second part of our tutorial, where I will show you how to access some parameters TASCAR from Matlab, but I will not use Matlab. I will use Octave because it's an open tool, so that's why it's basically easier to use it. So I will open another terminal and go open Octave, and maybe I will make the windows smaller so that you can see both of them in case things which we put in Octave will influence the scene. So first, what we have to do is we have to add to our Octave path, we have to add a directory where the Matlab tools that come together with TASCAR installations are located. So here we add this path, and in this directory there are several Matlab tools for TASCAR, and one of them the first one which I want to show you is used to influence various parameters of the scene. So in TASCAR we can influence or access the parameters of the scene using open sound control, and the function that we will use here is called send OSC. So we can look for the help of that function, and you can see there's a function send OSC, which is used to send the so-called OSC message, and it works in the following way. As you can see here, we have to specify the host port and address, and it's not very hard. So here we can see the command send OSC. The host and the port are usually those two default values. So we have local host and default port number, and the next thing which we have here is the address, and this address is the address of the parameter that we want to influence. And to check where did we take this address from, we can go back here to TASCAR and open the so-called OSC variables use, and here we have a list of all the addresses, all the parameters that we can influence using these functions. So for example, here, as you could see, we had cafeteria, Peter, position. So we already can suspect that this will be related to the object Peter in the scene. So here we have Peter, position, and these three letters here, they indicate that the parameter position will have to be specified with 3 float numbers. Also the case here, we have here 3 different numbers, and now let's go back to our map and let's see what happens with Peter when we execute this command. And you could see that the position of Peter changed. You can try the same thing with Kerstin, but we can send her where else. We can change the Kerstin. So you could see again that this position changed. Yeah, so with this we can influence not only position but also orientation, gain, and many other parameters of our TASCAR scene. Okay, so this was the first tool, and now the second tool, which I want to show you, is used so that we can play back arbitrary sounds via sources in the scene. So for that we the command window here, and for that we will use the tool which is called TASCAR, or first look for help for this, TASCAR check.io. And we can see that this function TASCAR check.io is used to for synchronous recording or playback via jack. So how does this work? So since the sources in the scene are also available as jack ports in jack audio, we can use this function to play back an arbitrary sounds via those sources. So to give you an example, first we have to generate an arbitrary signal. Let's say in this case we can generate a stimulus, which is, yeah, this is one stimulus that I generated before, which is a Gaussian noise, 3 seconds of a Gaussian noise. So here we have our stimulus, and then we can say TASCAR check.io, and as first argument we pass our stimulus, and this stays always like this, like output, and then we have to say via which jack port we want to play back this sound. And the jack ports, if you go back again to jack connections, we can see that that the sources in the scene will also be represented here as jack ports. For example, here we have this Kerstin 0.0.0 corresponds to this address here. And well, I will close this away, and now let's try it out. Here's something. Yeah, and yes, I hope you could hear this sound already with the reverberation added to it. So we played back this sound, this Gaussian noise within the scene. Other example might be, let's play a different sound, sinusoid. But for that we had still play it again. Okay, here, yeah, we need the time, and now we have a different stimulus, which will be a sinusoid. Yep, and now let's play it via Peter. Yeah. Yeah, so you could also see that this source has been active for a while we were playing this. Okay, so these were two tools I wanted to show you in the context of Matlab or Octave. So the important thing to notice here is that already with these two functions, we can create a experimental design where For example, we will play back various sounds, and we will also influence the parameters of the scene. One could, for example, imagine experimental procedure where we measure a minimum audible angle, and the position where we can influence each time the person answers a question. We can change the position from which the source is coming, and so on and so on. The possibilities are very different. It's just to see that just based on these two functions, we can already start creating more complex experiments. There's one more thing I would like to discuss with you, and then show you the tools for that, which is so at the beginning I told you that we would like to create experimental procedures that will be very realistic, where we could present some virtual acoustic environments to subjects, to our participants with or without hearing aids, and with those realistic environments we could create those psychoacoustic or behavioral test procedures. But also another way of evaluating the hearing or the hearing devices is the objective evaluation. So in this case, instead of creating experimental procedures for living participants, we can evaluate the performance of a hearing aid using another algorithm. Let's say by, for example, checking the performance of the localization algorithm, or like a machine learning algorithm, or objective evaluation of hearing aid benefit, of speech intelligibility, or maybe quality, or any other parameter. And still, for that objective evaluation, it's very important that we also get a realistic environments, realistic sounds that we can use for that evaluation. And of course, we can go into the wild, so to say, and record on the street and record various types of sounds. But the problem is that we don't have any control of what is happening there. And this is where TASCAR is very useful as well. So here we can, instead of going into the street and making a recording of all the complex sounds, we can actually create the street environment and also have an influence of the complexity of this scene. We can arbitrarily add and remove the sounds, or we can, for example, create various different rooms of different sizes, or we can also make the sources move with a predefined trajectories. So you can, I think you can get the point that we can create many different realistic environments, still by keeping the control over the parameters in this. So at this point, I will use this opportunity and show you one more nice thing about TASCAR. So here at help, we can open also a manual, and here we can see all the important things that we should know about TASCAR, or if we forget about how to create something in the scene, we can always go back to this manual and have a look how to do it. For example, here we have listed all the objects, and we, let's say, if we don't remember how to define obstacles, which I didn't talk about in this tutorial, so we can go there and we can see how to do it. And there's also a lot of information about various modules or that are used in TASCAR, and so on and so on. But what I would like to show at this point are these command line tools. So tools for creating, as I said before, tools for creating the sound material principle. So here with this just one line, of code that we can execute in our terminal. We can create a WAV file that will contain a sound material related to a certain TASCAR scene, which is very helpful, and it takes much less time than the scene itself, which also is an important factor. Also, we can do the same with impulse responses. So we can render an impulse response for any channel of our receiver that we define, and this is also done within one line of code. So as I said, these tools are important and very helpful in case of objective evaluation of any algorithm that is related to audio processing. Okay, so let's go back to the presentation. So this was the tutorial, and I showed you these different functionalities of TASCAR. And now here you can see this block diagram from the beginning of this presentation, and I hope you can you have now a bit better imagination of what TASCAR can do. So again, we can create arbitrary scenes, fit them with various sources of sound. We can control those scenes in different ways, and we can also reproduce the scene in many different ways. Okay, and here I would like to also mention some examples of applications, so some studies that have already been done and are published already that use TASCAR for various things. So the first two studies that I want to mention, they use TASCAR for creating only audio content. So in the first study, the authors measured how subject perceive source movement and how good is the spatial awareness of the subject for different settings of the hearing aid. The second study, in the second study, they created various complex acoustic scenes and virtual acoustic scenes, and they evaluated how big is the difference in objectively computed hearing aid benefit between the simple scenarios typically used in the lab and those more complex scenes. And as regards the audiovisual studies, first example is a study that where the authors recorded the subjects' head movements while they were listening to the scenes, and then they used these head movement traces to generate the sound material for objective hearing aid evaluation. And in the second study, it was pretty similar, but not head movements were recorded, but the gaze patterns were recorded while listening to a realistic scene. And then they evaluated what benefit could an algorithm which is based on gaze provide to a hearing aid. So that was the second study. Okay, and this is how we come to the conclusions of this workshop. And well, so as I mentioned at the beginning, hearing research needs interactive rendering of audiovisual environments. On one hand, to test the subjects in more realistic scenarios, or on the other hand, to evaluate hearing aids with more realistic sounds. And also it allows for creating a communication loop. So tests participants in communication loop. Okay, and then for that, at the Uni Oldenburg, the TASCAR tool was created, which is an open source toolbox that allows for designing interactive experiments. So it can render moving sources and receivers. It can also recreate room acoustic properties, and it can serve, and it serves in our lab as a lab session management tool. However, on as a last note, which we've also find it important to mention it, TASCAR is not a room acoustic simulator, although it's or not mainly a room acoustic simulator, although it also simulates room acoustics. It cannot be understood as the typical tool to create, for example, to predict the room acoustics of some auditorium. So here the focus is more on interactivity and real-time rendering. So with this, I would like to say thank you, and in case of any questions, you can contact myself or Gizo Grimm, and we will be happy to answer all your questions. Thank you very much, and bye.